In this lecture, we're going to define a couple and determine the moment of a couple. Here are two examples of couple, and in both examples, we have a pair of forces, and of those two forces, they have the same magnitude, F, but they are acting in opposite directions. And also, those two forces are not acting in the same line. They are separated by a distance, and we use the perpendicular distance d to describe it. So in statics, a couple is defined as two forces of equal magnitude acting in opposite directions separated by a perpendicular distance d. Let's take a look at the effect of a couple. So we said for a force, there are two effects. Force can cause translational motion, and force can cause rotational motion. How about for this pair of forces? Well, it's simple. The net force caused by this couple will just be the sum of the two forces. But since they are the same magnitude but opposite direction, so they will add up to 0, which means a couple doesn't cause any translational movement. The only effect of a couple is to produce an actual rotation. So this is the same way as when we drive in a car, we hold onto the stairwell. With one hand, usually we push with one hand and pull with another hand. And if we are applying exactly the same amount of force in each direction, then you will turn the stairwell into one direction. But you will never be able to move this stairwell from one location to another. Now let's take a look at the rotational motion caused by a couple. Let's find the total moment caused by this couple. Well, in this sense, this couple is composed of two forces, F and negative F. So we're going to do the calculation for force F and force negative F separately. So first, let's take a look at the moment about point O. And this point O is the point located in the middle of the two forces, which are separated by a distance d. So the distance from point O to each force is d over 2. And now the couple moment, or the moment at point O, or about point O, since this is a 2D moment problem, so we are going to use scalar approach. Moment about point O equals to, for the force F, it will cause a counterclockwise rotation. Magnitude is F, and the moment arm is d over 2. And for the other force pointing down, the magnitude is F as well, and it will also cause a counterclockwise rotation. So again, with the scalar approach, we use the magnitude of the force and the moment arm. So the magnitude of the force is still F in the direction, or the moment arm is d over 2. So the moment about point O will be F times d. And since it's positive, that means it's the same direction as the direction as the positive direction I defined. So that means it will be counterclockwise, and the magnitude is F times d. And this is the moment about point O. Now let's take a look at moment about point A. And this point A is an arbitrary point in space, or in this plane. And the distance from point A to this force F pointing up is d prime. And this is arbitrary direction, or arbitrary distance. This A can be closer to the couple, or can be further to the couple, or it can be between the two couples. So it can be any point. So we're going to use this letter d prime to describe the distance from A to the force F. And similarly, we're going to say this positive will be counterclockwise rotation is positive, and we're calculating moment about point A. And now for the force F pointing up, it will cause a rotation about point A, and the direction of rotation is going that way. That means it's clockwise. Therefore, we need to put a negative sign in front of the first moment caused by this force F pointing up. And the moment arm is d prime because that's the distance from the point A to the line of action of this force, d prime. And for the next force, the force pointing downwards, this force will create a counterclockwise rotational effect about point A because it's to the left of point A and pointing down. Therefore, it will be a positive moment, and the magnitude is F times the moment arm is the entire distance. So the distance will be, or the moment arm of this force pointing down is d plus d prime. We rearrange this equation or simplify it. We will find the F times d prime actually will be cancelled out. And the result will again be F times d. So this tells us a couple moment doesn't depend on the reference point O or A. No matter which point you choose, the couple moment will always create the same rotational effects, and the magnitude is always the force times the distance d, where d is the distance between the two forces. From the analysis, we can conclude that a couple moment is a free vector. The reason why we say it's a free vector because it doesn't depend on the reference point. No matter which point we choose from the space, this couple will always create or generate the same rotational effect. And it only depends on the magnitude of the force F and the perpendicular distance between the force, which is d. And we just did the calculation, choose the arbitrary point A, and we figured out the moment always have the same magnitude F times d. And we did example in 2D. In 3D, it will be the same. And we also did a calculation for the net force. So for the couple, the net force equals 0, means there's no translational motion, and the magnitude of net moment equals to F times d. So we are talking about the magnitude here. But keep in mind, moments of couples are also vectors. Actually, all moments are vectors. There are two approaches to find the moment of a couple. In a 2D problem, it's easier to use the scalar formulation. In scalar formulation, you need to determine if the moment is positive or negative, depends on the clockwise or counterclockwise rotational effect. And the magnitude of the moment is always the magnitude of the force times the perpendicular distance between the two forces made up the couple. And in 3D problems, sometimes it's not easy to find the perpendicular distance from between two lines in the 3D structure. Therefore, it's easier to use the vector formulation. And for the vector formulation, we need to find a position vector r. And then the r cross f, we will find the moment of the couple in vector form. And in this vector formulation, the cross product F is one of the force vectors, and R is the position vector that must end on this force vector. And it can be any position vector between these two force vectors. So which means we can do one example. So for example, if we have force F in vector form, if we have F is 1 I hat plus 2 j hat, and the other force negative F will be negative 1 I hat minus 2 j hat. And to find the moment of this couple, we can find one position vector and cross one force vector. And you have to choose, if this is the position vector, we choose this position vector R. If we choose the R ends on one of the force, or this R has to end on the force vector we choose to do the cross product, which means in this case, this moment M equals to R, this R cross the force it ends on, which is 1 I hat plus 2 j hat. Actually, it will give you the same result if we use another position vector and use the other force. Let's do another example. So we say this position vector can be any position vector between the two forces as long as it starts from one force and ends on another force. So let's say this is another position vector, we call it R prime. And if this is our choice, then the moment of this couple can be calculated using R prime cross, and this time since R prime ends on the vector negative F, so we need to use the negative F vector. So which will be negative 1 I hat minus 2 j hat. And both approach should give you the same answer. Let's see one example. We are given two couples acting on the beam with the geometry shown. And we're going to find the magnitude of F so that the resultant couple moment is 1.5 kilonewton meter clockwise. So if we can find the perpendicular distance between a couple, then the scalar approach is easier to use. So that's why for this example, we're going to choose scalar approach. And also for a 2D problem, usually the scalar approach is easier. So first, we probably want to identify the two couples, right? Couples are two forces of the same magnitude and acting in the opposite direction. So we have one couple in the horizontal direction, and the magnitude is 2 kilonewton. And also, we can find the direction is the distance between this couple easily, which is 0.3. So the moment of this 2 kilonewton couple will be calculated with 2 times 0.3. And we're looking for the magnitude of F in another couple. So the other couple is in the vertical direction. Again, they are perpendicular, they are in the same direction, in the opposite direction and the same magnitude. And we know the distance D is 0.9. So we already know the resultant couple moment is 1.5. So we can find the couple moment from each couple and add them together, equal them to 1.5. Then find the force F. Also remember, clockwise direction is also important for in the calculation of moment. So here in the given information, it said the resultant couple moment is 1.5 kilonewton meter clockwise. It is a clockwise moment. So here, I want to use a positive sign in front of this given information, 1.5. So I set this clockwise rotation as a positive rotation throughout my problem. So in most of the cases, or in most of solutions you see so far, the positive direction for the moment is set to be counterclockwise, right? And by convention, counterclockwise rotation usually is set to be the positive rotational direction. But again, for each problem, you can set up your own direction, rotational direction, positive direction. As long as you follow your rule, then your answer will be the same. So in this problem, I'm going to show you if I'm going to use the clockwise rotation as positive, what results I will get, and then you can compare my result with the one showing in the PowerPoint to see if the two results are the same. All right, so clockwise rotation is the positive rotation. Now let's take a look at the two couples. So for the first couple, the 2 kilonewton couple, clearly will rotate or create the counterclockwise rotation. And for this F, the couple moment with magnitude of F, it will create a clockwise rotational effect. Okay, so after we figure out that, we can find the net, the overall or the total moment. So the formula we're going to use is the scalar approach. So the couple moment equals to the force or magnitude of the force times the distance between the two forces. And also you want to figure out the direction, which we already did. So write that down, and that's the formula we're going to use. Now the sum of the moment or the resultant moment, set up the positive direction. The sum of the moment by the two couples. The first one is the 2, but again, when we set the clockwise rotation as positive, now the 2 kilonewton couple will generate or cause a negative counterclockwise rotation, and the magnitude will be 2 kilonewton, which is the F times D, which is 3 or 0.3 meter. And the couple with F magnitude will cause a clockwise rotation, so it will be positive, and the magnitude will be F times D, which is 0.9 meter. And overall, this resultant moment should be equal to the value given in this problem, which is 1.5 kilonewton meter. So now we have this equation with only one unknown, which is the force F. Solve for F, the problem is solved. And F is 2.33 kilonewton. The second example, we have a 450 Newton force couple acting on the pipe assembly over here. And we're looking for the couple moment in Cartesian vector notation. So since we need to find the couple moment in Cartesian vector notation, so it will be easier to use the Cartesian the vector formulation, where we have the moment of a couple equals to a position vector cross the force vector, and the position vector should end on the force vector we choose. So to use the cross product, first we need to find a position vector from one force to another, and it can be any position vector, and then we find the vector form of the force. So here will be the approaches we're going to take. First, we're going to set our vector, position vector, between two forces. We're going to use RAB because that's the easiest way. And also, we're going to use the FB, since force position vector or RAB end on the force B, which is the force applied at point B. So you have to use that force in your calculation and use the cross product to solve for the moment. First, we need to write the position vector RAB in vector form. So this RAB is parallel to the x-axis, and that means it only has an x component. Or you can do the imaginary path method, where we go from the tail of the vector to the head of the vector, and we only need to travel along the x direction, and the distance we travel will be 0.4 meter. Therefore, this RAB is 0.4 I hat. And next, we need to find the vector FB in vector form. And we already learned or practiced this many times with this direction or slope triangle, 3, 4, 5 slope triangle. And also, if you take a closer look for this first FB, is actually within the ZY plane, or this plane is a ZY plane, which means that this FB doesn't have any X component. So X component, or the I hat term for FB, will be 0. X component 0, and Y component is the component that is parallel to the Y direction. In the slope triangle, value is 4. So 4/5 times the magnitude of FB. That's the Y component. And Z component is pointing down. Therefore, the Z component is a negative value. And the magnitude is 450 times 3, which is the vertical slope triangle, the slope triangle that is parallel to the z-axis, 3/5. Okay, so this is the force vector in the vector form. Then we're going to apply the cross product between the two values we just got, and the final answer will be the moment in Cartesian vector form.